Hi, Professor Welling.
Can you hear me?
Yes.
Finally. Sorry, I had some trouble getting into this system.
Oh, no worries. Actually, I just wanted to tell you that Professor Kanedakis won't be able to join us today because he's flying back from Denmark to Boston today. So he had asked me to apologize on his behalf to both of you. But he would be actually seeing the recording which we will be putting up on YouTube.
All right, fantastic.
Okay, so I'll introduce you to the audience and then we can get started from there. So hello, everyone, and welcome to this week's Crunch seminar. Our first talk today is a joint talk by Professor Max Welling and Johannes Brandstetter. Johannes Brandstetter has done his PhD studying Higgs bosons decay at the CMS experiment at the Large Hadron Collider at CERN. In 2018, he joined the Sepp Hochreiter's group in Linz, Austria. In 2021, he became an Ellis postdoc at Professor Welling's lab in the University of Amsterdam. Since 2022, he has been a senior researcher at the newly founded Microsoft lab in Amsterdam. His current research interest comprises of geometric deep learning, neural PDE solving, learning to simulate, and dynamical systems in general. Professor Welling is a full professor and a research chair in machine learning at the University of Amsterdam, where he directs the research group AM Lab. He is also a distinguished scientist at the Microsoft Research and the director of the newly founded Microsoft Research Office in Amsterdam. He is the fellow at the Canadian Institute for Advanced Research and also at the European Lab for Learning and Intelligent Systems, acronymed for ELIS, where he serves on the founding board. His previous appointments include VP at Qualcomm Technologies, professor at UC Irvine, postdoc at the University of Toronto and UCL under the supervision of Professor Jeffrey Hinton, and postdoc at Caltech under the supervision of Professor Pietro Perona. He finished his PhD in theoretical high-energy physics under supervision of the Nobel laureate Professor Gerard 't Hooft. With that, please join me in welcoming both of them for the talk. You may want to share your screen, Johannes, and then Professor Welling may want to begin.
Yeah, maybe I'll just start sharing my screen. Is that because I have my slides over here. So can folks see this?
You can see it, yes.
All right, so I'll just do a brief introduction. And in fact, I may have to log off halfway through, so I apologize for that because I have some other thing going on. But I'll just do a brief overview introduction as agreed. The main and in-depth technical talk you'll hear from Johannes. And so I'll be talking about transforming PDE solving via machine learning. No, of course it doesn't move forward. Okay. So I'm not sure this audience what their background is precisely, but I'll be introducing a little bit of machine learning, just a tiny little bit. So machine learning has been on sort of a success roller coaster starting around 2009, 2010. The first application that succumbed to deep learning was speech recognition, which until that time, 2010, around that time, was plateauing. There wasn't a lot of progress in terms of word error rate. And then when deep learning was introduced by the group of Jeff Hinton, the error rate started to drop steeply until basically a low number so that you can now talk to your phone and your phone actually understands what you're saying. A similar thing happened in computer vision around 2012, where there was a sort of a competition called ImageNet, and the competition, the error rates were about halved by, again, a deep learning model, AlexNet, from the same group in Toronto. And these days, it's basically one sort of success story after the other, you know, ranging from, you know, playing chess and Go to explaining jokes to generating images, completely new creative images from prompts. And these days, actually, even videos created from prompts. What I'm excited about, and what we are excited about at Microsoft Research, is applying all these techniques ranging all the way from reinforcement learning to, deep learning classification and regression, all the way to generation on scientific data. And we have seen a few sort of stunning examples already, not from Microsoft Research, but we have just started, and new results from our groups are starting to emerge, but other groups have already been in this game for a bit longer. And there's, of course, the famous result AlphaFold by DeepMind, where an amino acid sequence gets folded into a three-dimensional structure, and a result from EPFL and DeepMind on how to control plasmas in a tokamak reactor. And this result here is from Amsterdam, where we're using these diffusion models, which are also used for image generation and video generation, but now for molecular generation. And here you can see how out of sort of a noisy ball of sort of atoms, you can sort of create basically stable molecules. So the technology of the workhorse that's behind all of this are versions of CNNs, convolutional neural networks, or graph neural networks. With a twist sometimes, like where we build in symmetries, which is particularly important for scientific applications, which we call equivariant neural networks. Now, a neural network is basically a bunch of, or convolutional neural network is basically a bunch of filters that we run over an image or a sequence of something. Sort of, we do this many times, where we also have operations like pooling and nonlinearities, which are in between these things. In the end, we have a very large stack of latent variables or hidden units, activations, which are then fed into a usual classifier to classify what's in the image, and we backpropagate through the stack to adapt these filter values in order to improve the system, which is then called learning. Now, you can think of convolutions actually as message passing algorithms, where the neighbors send messages to the central node. Actually, also the node send a message to itself. And this view can be easily generalized to graphs, where now the graph is irregular instead of grid-like, but also the number of nodes can change, which requires us to do some changes to the architecture. But there's many interesting developments in this, and nowadays we can do message passing or graph neural networks, graph convolutional neural networks quite well. So here's an architecture that was actually developed by Johannes and co-authors, where we basically make this whole architecture equivariant to symmetries. So that basically means the following: if you rotate your head, or if you basically feed the numbers into this neural network in a rotated reference frame or translated reference frame, the neural network doesn't get confused. In principle, it does exactly the same as it did before, but then in a rotated way. So that's what we call equivariance, and it's very important, of course, because we know the physics of the world doesn't change depending on where we do the experiment or in which orientation we do the experiment. Well, subject to, of course, gravity effects and stuff like that. Now, what we are interested in is PDEs and scientific applications, which span a huge spatial temporal scale, all the way from picometers to light years, and from femtoseconds to giga years, enormous scales. Yet, surprisingly, many tools that we use span these enormous scales, and basically it's ordinary differential equations and partial differential equations which rule the world in almost all scales, all the way from Schrödinger equation to astrophysics and the way that galaxies collide. So yeah, PDEs is the tool that we are interested in, and we are interested in trying to use the modern deep learning technology to better solve these PDEs. And again, there's a huge range of things where this could be applied if we are going to be successful at doing this. Now, we are very, very well aware and humbled, in fact, by the fact that this is a very old field. Hundreds of years, people have written books about it. This field is hugely developed. So who are we to come in and say that we can do better? Well, of course, we can do better, but we can offer a new tool to the toolbox. Numerical solvers have many requirements and many dimensions on which they are optimized: accuracy, stability over long rollouts, speed, computational cost, ease of use, uncertainty, and generalization across a whole bunch of dimensions, such as initial conditions, boundary conditions, PDE parameters, integration, grid resolution, regularity, geometry, topology, dimensionality, and probably many more. we are mostly going to tackle and try to attack the problem of speed of solving things at the same accuracy, or maybe even better accuracy, but typically at the same accuracy, but trying to accelerate. And that's important, for instance, if you want to predict, let's say, the climate in a century at a very high resolution, current technology doesn't allow you to do it. Or if you want to design a new tokamak reactor, you want to simulate the plasmas inside the new tokamak design very often. And of course, here also you want very fast solvers. So basically, we're going to think of a solver as a differential iterative program where we optimize these hyperparameters from data. This could be simulated data by a numerical solver, but it could also be real observations. And the key question basically is that we have to ask ourselves, if we first have to generate data and then train a PDE, we have to make sure that this solver actually generalizes to new initial conditions and new boundary conditions or new parameter perturbations or even new dimensions. That's the key question. Otherwise, it's quite pointless to do this. But the way I think about it is as a sort of, sustainable way to do experiments or, to run your numerical solvers. You don't throw that data away. You store it, and from that, you train a machine learning model. They could, in principle, shortcut the computation, do it faster if you get in the neighborhood of your previous solution. If it's very far away, you probably have to raise a red flag and say, listen, you have to go back to your numerical solver. So again, the key point is this generalization. In machine learning, we often call this underfitting and overfitting. On the right-hand side here, on this side here, we are in the regime of very many parameters relative to the data, so very flexible models. And on this side of the spectrum, we have injected a lot of inductive bias about, let's say, the problem that we want to solve. And in fact, so we have injected a lot of inductive bias, and we have little data compared to the number of parameters of the model. Sorry, a lot of data compared to the number of parameters of the model. So on this side, we are slow because we have a numerical solver. We have error guarantees. We have few parameters. We have large inductive bias, no data or little data, and hopefully good generalization. On this side, we have the opposite. Very flexible models, no error guarantees, but fast solving. Lots of parameters, little inductive bias, lots of data required, and we don't know quite yet about generalization. So there's been a few attempts and different approaches to try to inject machine learning in these solvers. I won't go into a lot of detail because of the time. So this one is from Hoyer's group. It's one of the first ones where basically they train the stencils that approximate the partial derivatives in a normal solver. And they find that, for instance, in Burger's equation, if you have the shock waves, that close to these shock waves, different stencils for the same derivatives are optimal versus if you're in another regime. And so you have these adaptive stencils that approximate these derivatives, and they learn them. Another one that's probably very well known to this audience are these physics-informed neural network-like approaches, where you stick in the actual values of the space-time coordinates, you push them through a neural network to produce the field variable, you backpropagate to get the derivatives, and then you have some kind of error which tries to reduce the actual PDE versus the one that you get by using your neural network. That's a constraint, and you try to minimize it, and that way you can sort of learn unsupervised a neural network that produces for every x and t the field variable. And you can also add other things about the initial and boundary conditions as well as supervised learning signal. And so the final thing I will discuss here is neural operators, also very well known in this audience, which basically is a mapping from one solution to the next solution. Let's say one image to image, or basically regressing through time. The method tries to formulate this in terms of operators, so basically grid independently, independent of grid sizes and resolutions. And there's of course also apart from the deep UNet, there's also the Fourier neural operator approach, which uses Fourier transforms to achieve this thing. Johannes and I and others have also and Daniel Worrell, I should say, have also contributed something in this sort of regime where you map sort of a solution autoregressively forward in terms of graph neural networks. Another thing we did, which might be interesting to look up, is handling data sparsity through exploiting symmetries. So these PDEs have beautiful symmetries which map one solution to another solution, and you can actually compute them. There's programs to do that, and using that you can augment your data set to a much larger data set, and that's very helpful for stability and generalization. Okay, so I'll conclude here. Will machine learning play an important role? Is this a new paradigm shift in this field? I hope so. I think so. I believe so. There's important challenges as always. We don't have really error guarantees, which means that for many applications, maybe people don't trust it. There's the deep learning needs a lot of parameters. So there's the data sparsity issue, generalization. Do they generalize to new situations, new initial conditions, boundary conditions? Can they be made stable for long rollouts? Can they handle multi-scale problems? People haven't really looked in that, I think, and non-regular grids, etc., etc. I would say there's a spectrum of methods, all the way from traditional solvers, all the way to completely data-driven deep learning, surrogate models, and you can sit anywhere in that spectrum, which has advantages and disadvantages. And one important thing to figure out is where should you be on that spectrum? And I'll stop there and then head over to Johannes.
Sorry, can I ask a quick question?
Sure, if we have time.
Hi, Max. I'm Nat Trust from Sandia National Labs. So I'm curious. You mentioned equivariance as structure preservation, which is more of an image processing type of symmetry. But for PDEs, there's a lot of other things like gauge symmetries and other kind of physics structure preservation. So particularly because you mentioned tokamak dynamics, where all of these are very, very crucial in the forward simulation world. Can you comment on that and what kind of thoughts you have about structure preservation there?
Yeah, so this is a really good question. I think we haven't really even scratched the surface on this. So indeed, there are very sophisticated symmetries, including sort of also, I guess, gauge symmetries, as you mentioned. We haven't been able to build them into the solver so that they are automatically respected. At this point, we've only been able to use them to generate more data and then use that data to train the solver. But it would be much better if we could, in fact, sort of build them into the actual neural network themselves. Now, there's also conservation laws which might result from these symmetries. And again, and I haven't really even gotten to the bottom of, how that's related in the sense of whether for every symmetry you can come up with a conservation law and whether we can build in the conservation law into the solver. But these things all need to be explored still. I think it's a widely open field.
Great, thank you.
I think we move to Johannes now.
Yeah, we can do that.
Yeah, so thank you very much for, I never got such a nice introduction, so I don't have to do the first slides myself now. I will try to use the rest of the time to speak about two papers we did recently in our group. And the first one is how to better basically exploit the structure of underlying fields and interaction of these fields. And the second one is basically a generalization or using the generalization capabilities of modern architectures from computer vision and what these architectures are able to do. And with that, I want to basically continue with one of the last slides Max showed, and that's the operator learning method. So as Max said, you're all very familiar with operator learning methods, especially if we look at the general description of deep O-nets, where you have the branch net, which can basically be any neural network or any deep neural network architecture. And then we have the trunk net, which where you get the inputs, for example, the coordinates where you want to get your output mapped to. And in most of these works, we basically think of mapping from a specific grid to another specific grid. So the grids are basically fixed, which means that we try to optimize the trunk net with whatever capabilities we have. And then there is a second question, and namely that the operator, so to say, should be able to generalize not only across grids, but also across equations, for example, different parameters of equations or different timescales and so on and so forth. That's the question we are trying to tackle at the moment. Of course, the next question would be, and I find it quite interesting to read this paper about the comprehensive and fair comparison of these operator methods to test it really on problems on non-regular domains or different boundaries and so on and so forth. But for most of this, for the approaches we are talking about, we can really think of an image-to-image modeling approach in the broadest sense, where we have a bunch of feature maps which we try to extract into the hidden space and then try to extract the dynamics from there and model the dynamics up to the next time point. And that brings me to the first paper. And this paper starts from an observation that if we, for example, look at weather data, and this is a very simplified weather model, where on the left we have a scalar pressure field, and on the right we have a vector wind field. So that means that the left field can be represented with one channel to a neural network, and the right can be represented with two channels. So usually we would put that into some kind of convolutional UNet network by injecting like 3-channel input dimension. But there is much more to that. Namely, if we think of the scalar pressure field to change according to some pressure gradients, then the wind starts to flow into these low pressure regions. And of course, the wind changes, which again makes the pressure field change. That kind of means that there is a very, very close relation, not only between the components of the vector field, but also between the two different fields. And this is something which kind of made us think. And that gets a bit more clearer if we basically look what Fourier neural operators are doing, because this is a nice tool to really visualize what is going on. So Fourier neural operators, they basically, via Fourier transform map into this hidden space, do the linear transform there and map back. So the whole thing can also be achieved with convolutions with very wide filters. But for me, it was very interesting basically to look at Fourier transforms just as mathematical operation, and always have this in mind that you do a mapping into this function space, a linear operation, then transform back. Because we started to build a very, very easy toy example, and that's a kind of a vector field. So if you're familiar with deep learning frameworks like PyTorch, you would present this data in a form like you have one batch dimension. Obviously, you have two channels, since each of these errors has an X and Y component, and then you have a grid of in that case 32 times 32. So how would you feed that into a Fourier neural operator or into just a Fourier transform? You would use two channels, and for each of these channels you would apply a Fourier transform. And that's exactly what we did. We applied a Fourier transform to each of these channels, and then in the hidden space we applied a random matrix multiplication, and then we did the back transform. And what it seems is that basically the structure is like really kind of lost, and it's really hard to think how this right and the left image are related. And the reason why it is hard to find this relation is because the modes basically for the X and Y components were treated separately. So another next and obvious choice is to not treat them individually, but to treat them as one object. And how you can do that? You can basically use the Y component as the complex component of a complex number. So instead of inputting two fields of real numbers or floating point numbers, we can input one field of the type complex. And that means that our input dimensions have changed to of course again one batch, but now one channel, which is of type complex, and the spatial dimensions are again 32 times 32 in that case. And if we apply the same thing, if we do a Fourier transform into the hidden space, apply this random weight matrix and do the back transformation, we now see suddenly that the structure is much more preserved than it is on the left, than it was before. And this is something very encouraging, because for me, this is a bit like if you slide a filter across the image, you still distort the image, you extract information, but you do not completely change the image within one layer. So that was basically the starting point for this work. And we basically tried to understand how to build such transformations over vectors. And then we stumbled upon Clifford algebras, because they basically have this power to describe objects not only as scalars or vectors as we usually know, but as so-called multivectors. So such a multivector here on the very right consists of a scalar part, consists of vector parts, which are our standard Euclidean vectors, but also as higher order objects such as bivectors and trivectors. These bivectors are plane elements, and usually a typical bivector would be a cross product. That the output of a cross product is a bivector, although represented as a vector, it transforms differently than a vector does. And I was hiding the fact a bit that this is in 3 dimensions. So in 3 dimensions, we have our 3 basis vectors, we have 3 bivectors, and we have 1 trivector. In 2 dimensions, we only have 2 base vectors, 2 and 1 bivector. And these Clifford algebras have these nice properties that you can do bilinear operation between the so-called multivectors. And these operations are done by the so-called geometric product, which basically uses two multivectors as input, combines them in a predefined way, and outputs another multivector. And that's basically very encouraging, because these are now the 2 components we need. First of all, we have a way of representing such high-dimensional data as one object instead of individual channels. And then we have an operation which basically takes 2 of these objects and produces another object. And that's exactly what happens in neural networks, because we can now, instead of using the scalar multiplication as it is used, for example, in convolution layers, to replace it with this geometric product, which maps one of these multivectors to another multivector via, for example, a multivector filter. And that's exactly now what we're doing. So we are defining 2 operations. One is the so-called Clifford convolution, where we think of our input fields now not only as a bunch of channels, but as a bunch of multivector channels. And each of these multivector channels has individually, in 2 dimensions, 4 components. 1 for the scalar, 2 for the vectors, 1 for the bivector. In 3 dimension, each of these multivectors would have corresponding 8 components as shown before. So we can group our fields now as this stack of feature maps, where each feature map corresponds to the scalar, to the x component of the vector, to the y component of the vector, and so on and so forth. But if our input fields have this characteristic multivector structure, our kernels should also have this multivector structure. And this is what is going on here. So we visualize these multivector kernels such that they also are grouped together in these multivector objects. And as you normally slide your kernels across input fields, you slide your multivector kernels across these multivector input fields. And what happens? You get multivector output fields. Again, a stack of different multivector fields. That is a way of how you define a convolution over such multivector fields. There are other ways, but this is the most general way. It gets really interesting if you try to define a Fourier transformation, which was like the starting point of this work, as I showed with the vector field before. Because what you can do with the multivector here written for 2 dimension, the same holds for 3 dimension. You can write it out with this base component. So the E1 corresponds to the vector in x dimension, the E2 the vector in y dimension, and the E1, E2 to the to the bivector. The bivector in 2 dimension is the so-called pseudoscalar, because if you square this bivector, it squares to -1, and this pseudoscalar is written with I2. And then you can just do a bit of a juggling around with indices, and then you end up with this expression, which is basically the very same as on the left, but just split into 2 parts, where one is a part which transforms like a spinor, so it has a different transformation under reflection, and one part that transforms like a vector. And the interesting thing is that since these objects, so these so-called pseudoscalars, that they square to -1, these both of these expressions have exactly the behavior of a complex number. And that means that we can do a Fourier transform over this whole multivector by doing 2 individual Fourier transforms over 2 complex fields and adding the modes together in the Fourier space. And that's exactly what we did. So we again have our bunch of fields of multivectors. We split them into 2 different parts, the spinor and the vector part. We do 2 complex Fourier transforms, and we add the modes together in the Fourier space. We can do weight multiplication there via the geometric product. We can skip the high frequency modes, and we can transform back. The interesting thing is what I showed in the very beginning is exactly this part. So that's how you can complexify basically a vector field by putting the x component here and the y component as a complex number. And that brings me to the experiments. So we tried to frame the experiment such that the coupling, which was the initial motivation for this work, so the coupling between these 2 fields, gets stronger for the experiment. So we start with the Navier-Stokes equation, where the coupling, so this is the vector field so the velocity field, and then we have a scalar field that can be some smoke transported along this vector field. And the coupling between these 2 fields is, I would say, rather weak and described by this external force term. The second one is the shallow water equation, which we showed at the beginning. And there the coupling is rather strong because we have 3 coupled PDEs, and basically the connections between vector and scalar fields is much stronger. And the strongest and my favorite one are the Maxwell equations. These are done in 3 dimensions because the Maxwell equations have this intriguing property that they have an electric field and a magnetic field, and the magnetic field is the dual of the electric field. So the magnetic field can be written as bivectors, meaning that you can fill up a whole multivector in 3 dimensions, where you put all the electric fields into the vector part and all the magnetic fields into the bivector part. And performance-wise, it really showed that that all these Clifford counterparts perform better than their non-Clifford versions. But also, if you increase the coupling of the problems, so if you have more coupling between vector and scalar fields, the advantages got bigger, and so the performance increases is better visible. And these plots are shown for the Maxwell equation, where really the orange is Clifford for low number of trajectories, and black is the standard Fourier neural networks, and the difference, especially for low number of trajectories, is really huge. And that is just the better inductive bias the Clifford layers bring into for such kind of problems. And speaking of inductive bias, there was one very interesting thing for me to realize, and that was where I basically really started to think of inductive bias very strongly, because if we look at the ResNet results, maybe I forgot to say that we use 2 architectures to ablate. The one is a plain ResNet, and the one is a Fourier neural operator. And the reason why we chose these 2 architectures is because they are mainly built out of these convolution layers and mainly built out of these Fourier transform layers. So we don't really have to care so much about normalization and residual connections and all these parts of modern architecture, but can really focus on the layers itself and ablate them to their non-Clifford counterparts. But for ResNet, it seems that, which is not like as strong as a solver as for example, the Fourier neural operator, it seems that, again, getting on the left is large number of training samples, and on the right is low number of training samples for 4 different tasks. And if we go from the right to the left, we of course see that the performance increases, so that the error gets lower. But we also see that at a certain point, really the Clifford parts, which are shown in yellow and orange, overtake the green one, which is the baseline, which is not the case for a low number of trajectories. And the reason is really that the resonance as a solver itself is rather weak. So it rather fits, or it rather smoothens the data, and is not capable of basically accepting that there's a lot of inductive bias. So it takes some trajectories to get the solver into a reasonable range. And whenever this is reached, you really see the inductive bias. That is what was very interesting finding, because apparently you need a strong enough backbone network to really get the advantage. Okay, and that is exactly what brought us, so my colleague Jayesh Gupta and me, to the next questions we were asking, because we were really seeing how important these strong backbone networks are. And at that point, we were really looking a bit into what is going on into computer vision, because, well, we see these all amazing results around us from image generation, and very recently video generation, which are basically done by diffusion models in various forms. And for this image and video generation, these diffusion models have a second partner in crime, and these are the UNets. So UNets are really the driving horse between this very elegant algorithm of diffusions. So the question is basically, how strong are these UNets, and how do these UNets do on PDEs? And for that, we basically have a closer look. And UNets have 2 properties which are extremely nice for this image generation. First, they have this difference of treating local information and global information. So they start with local information, and then the downsample towards a more global treatment of information, and then they do upsampling. And what is also very important for this image generation is this so-called conditioning. So especially if you think of this, where you input a text prompt and you get out an image, you basically need to feed this text prompt via some representation to each of these downsampling and upsampling blocks. And this is done by very extensively researched conditioning tricks. And this conditioning tricks is exactly what you can also use for PDE modeling, because, well, this is exactly how you feed information of equations or of time horizons into your equations, into your solvers. And if we compare these UNets to Fourier layers and information flows in Fourier layers, basically what the UNet is doing in the whole architecture, a Fourier layer is doing in one a Fourier architecture is doing in one Fourier layer. Namely, it has different modes, where global modes where low modes correspond to global information, and higher modes correspond to more localized information. So one basically splits the signal into global and local information with and the whole variety of modes in between, and then modifies this information such that basically the input is mixed and changed. So again, the UNet uses local filters at the bottom and more globalized versions at the local filters at the top and more globalized versions at the bottleneck layer, whereas F&O layers do that within one go. So that's of course the question now, how this compares to each other. And there was another interesting thing, and that is if you look at computer vision, how you usually should do downsampling, you should not do downsampling by just using, as it is done here, every 4th or every 8th pixel, because what you then end up with are these so-called aliasing effects, because you have the information from much higher resolution, namely these are really the original pixels, but you just have them at every 4th position, which results in a very weird looking image. But if you do so-called band-limited subsampling, so if you go to the Fourier space, cut away the higher frequencies, and then go back, and based on this band limit image, do your subsampling, you end up with an image which is much easier to recognize if compared to this naive subsampled image. And that is one of the motivations we had to ask ourselves, maybe we can use UNets and augment UNets in the downsampling path with these Fourier operations, which do exactly the same thing. And for that, we did it really an extensive ablation of architectures. So we had the ResNets, which basically are characterized by having no local and global information flows, dilated ResNets, which over the dilation of the convolution layers aggregate more global information, many different versions of Fourier neural operators with different numbers of layers, different numbers of used modes, and many different versions of the UNet, from the original 2015 UNet until some own baseline UNets, and then some very modern UNets, which basically really come from this diffusion models, modern UNets with attentions, and then all these UNets where we combine them with Fourier blocks in the lower layers. And we test them of course with different parameters. We test it on forward and backward runtimes, which is very interesting. Basically, these ResNet and dilated ResNets take the longest to train. We test them with peak memory usage, and for all these measurements, it seems that these UNets, they do very well and can be scaled up to much more parameters, which is of course not surprising because, well, that's what people in computer vision do. But what was a bit surprising is looking at the results, because whatever equation, maybe I should also say that we tested on different equations. We tested on Navier-Stokes equations in velocity and vorticity formulation, shallow water equation in velocity and vorticity frame, but we also tested on this conditioning, which I will say later in a few slides. And what was very interesting is that whatever we basically looking at, all these UNet variants perform extremely well. So we have here many different lines, and it's probably very hard for you to disentangle them. But you can think of that everything here on the right, which is the highest number of trajectories we used for training, is some sort of UNet architecture, either with attention blocks or with Fourier layers in the downsampling. Whereas everything here in the middle is some Fourier-based blocks, and everything on the left is some ResNet blocks. Whereas the dilated ResNet do a fairly good job, but being slow. Exactly. And for a low number of trajectory, basically everything kind of smoothens out. And that brings me to the last part, and this is the conditioning. But before we look at some very nice plots. So this is the best UNet model we have. So we have, for example, here the ground truth data. So this is the ground truth scalar field for the Navier-Stokes equation. This is the ground truth x component of the velocity field. This is the ground truth y component of the velocity field. And we see that if we propagate this forward in time, this UNet can really capture the dynamics also visually very well. So, and now we come to the parameter conditioning, and here the task was really to start with the same input, so that the same input fields like velocity field and scalar field, but additionally to this input field, tell the network on which parameters it should condition. And the parameters we condition on were like the buoyancy force, so how much the scalar field is affected by a buoyancy force, and the time window, how much you should predict into the future. So if you look on the left plot, everything here is done for a buoyancy force of 0.2, and all these, basically every of these predictions is obtained from the same input, but with different for different time windows. So that is a small time prediction to the future, that is a medium range time prediction, and that is a large range time prediction to the future. And we see that all these predictions very well match the ground truth. And that basically means that the UNet has learned to really condition very nicely on these parameters. And we can do this for much longer time horizons, and of course for different parameters, as it is shown on the right, where basically we have exactly the same model, but now with a different Bayes C-force. So starting points are again the same, but for this different Bayes C-force, we again get for different delta T's, different behaviors, which is exactly, or which is fairly well captured by our model. The higher Bayes C-force is a bit harder to model, and therefore we see that the model is not hitting it so exactly as it does for the low Bayes C-force term. In general, if we basically look at the interpolation space, so this is the force magnitude we were training our network on, UNet variance did very, very well with a small MSE error. For Fourier variance, it was a bit hard to get this conditioning to work. We tried different things of conditioning information in the Fourier space, in the spatial domain, and both together, which in the end seems to work best. But this is again where the UNets have real their stronghold, and this is not very surprising, since well, we know this from diffusion models and computer vision. And that basically brings me to a short recap. So what I tried to basically talk after the nice introduction from Max, how we currently try to get more geometry and structure into the PDE modeling before even trying to use the full power of operator learning to generalize across grids and to boundaries. We have introduced these Clifford layers to enforce structure, which is of course a very interesting project which we're currently working for updates. And then we really studied this design space of how to build local versus global information flow architectures, where one of the big messages we're trying to convey is that we really need good baselines here. So we really need strong baseline models on which we try to improve. And that's of course what we try to provide for the community. So we will release a PDE arena, how we called it, which is a big open source project where we have all these different solvers implemented with all these data sets provided, and then people can try themselves to make them better, to find the errors we are doing, and correct us if possible. But we are fairly confident that these models work as reported. And of course we will try to release very soon a package on these Clifford layers as well. One thing is of course very imminent, the question, why don't we build Clifford UNets? And that's exactly what we're doing right now, and that's what we will also be adding to this PDE arena as soon as possible, because this is of course exactly in this combining these two researches. But building a Clifford UNet is much more challenging, because you have normalization and so on and so forth. So we really try to do that properly to really provide a good baseline for that as well. And that's my last slide. So most of this work is done together with my colleague Jayesh Gupta. And if you want to contact us, these are our email addresses. And with that, let me finish here.
Thank you, Johannes. We can wait for questions from the audience.
I hope I stayed in time. I tried to be quick.
Yeah, absolutely.
Hi, Johannes. This is Son from Carbon. Nice talk. Thank you. All of these experiments that you showed today are data-driven, right?
Yes.
Any thoughts into kind of physics informed, how this can impact kind of unsupervised learning of PDEs? Because one challenge is to kind of generate those data using high fidelity simulations.
I very much second this question. That's a very good point. So the design space of or the problem space is huge, right? And we really picked one of this problem space to make this trunk network better. And basically that we did by data-driven approaches. Of course, the next challenge is really to use these equations and try to get kind of similar performances without using data or without using so much data. But that is definitely on our to-do list, as well as a better generalization over boundary conditions and so on and so forth. But I fully agree that is all purely data-driven.
Thank you.
This is a really excellent talk. I want to put a paper in the chat. We have a postdoc who did a lot of work with Fourier, you know, a variant of FNO, but in doing inductive physical biases like conservation and things like that. I'm really curious whether you think with the Clifford algebras, there's a similar potential for doing that kind of thing. You know, a lot of things like isotropy, all sorts of stuff along those lines. Is there anything you can speak to that?
Yes, so basically all you can do with normal networks, you can do with Clifford algebras too. I see Clifford algebras more as having a better grouping, because what was basically driving in the computer vision community was this localized filtering, and we extend that to another dimension via this multi-vector viewpoint, so that you really have basically a multi-vector filter which groups together objects. But all the things you can do, introducing symmetries, so equivariance, introducing conservation laws and so on and so forth, you can do that the standard way. And that's of course the way we hope that it works, because you already have this physics quantities a bit better grouped together. And maybe also to the previous question, one of my hopes is that if you do like a physics informed loss on something which has gradients with respect to vector fields, and your output is naturally presented by these vector fields which come off this algebra, that the gradient loss flow and that the training of these architectures gets easier because you have it already tracked in your network. If this answers the question a bit.
Yeah, maybe one specific thing. So for Fourier operators, right, the key thing is that you're encoding an operator in terms of a symbol, right? And a symbol has a clear tie to a differential operator or a pseudo differential operator. Can you comment on what kind of differential operators or like physics objects are naturally described in terms of the Clifford algebra?
I mean, that very much depends which Clifford algebra to pick, right? I mean, you can pick the easiest Clifford algebra, and that's basically complex numbers. And then you can describe objects which are complex numbers, which just have yeah, or you can go higher to much more expressive Clifford algebras, and for example, electromagnetic fields and such objects are described by three-dimensional Clifford algebras. But objects like curls and so on and so forth are described by bivectors, so by elements of the two-dimensional Clifford algebras. So it very much depends on which algebra to pick, which objects to describe. But I would need a concrete example to give you an algebra, basically.
Yeah, maybe I can follow up with you offline. Thank you. It was a great talk.
Maybe we could hear from Lulu. He's the one who has developed deep operator networks. So maybe we could hear from him. What's his thoughts?
No, I think this is really great work. And also I'm interested to look at the GitHub page. So just let me know when it's online. I will be interested to have a check.
That would be nice, and then we can start building different models from there. Yeah. So I think the regular grid is just the beginning.
Sure.
We have another collaborator of ours. She develops a lot of FNO related stuffs, Dr. UAU. Maybe she could tell us something if she has some thoughts on this. UA, you're online?
Okay, yeah, hello, can you guys hear me?
Yes.
Yeah. Oh, let me see. Oh, yeah. Hello. I'm Yue from Lehigh University. Yeah, great talk. I literally learned a lot. Yeah. So I think this is very interesting topic, and yeah. So I just want to briefly mention that we have recently developed a graph neural operator. So basically, yeah, and for that, and we have been following, Dr. Welling's work, and we have been trying to use the equivariant idea to develop a conservation law kind of preserving neural operator. So yeah, so we are probably going to post that. We already submit that to AI Stats. We are probably going to post the to archive soon. And so we have learned a lot from the talk, and also basically the general work we have been following from Max and also Johan. Yeah, thanks a lot.
Very exciting.
Yeah.
Do we have more questions for Johannes?
I have one. Sorry. Thanks, Johannes, for the talk. This is Anthony Gruber. I also work at Sandia. I do some work with Nat's group. I was curious, when you do these Clifford algebras, you essentially have, like, if you represent each channel as a whole element, you essentially have like 2 to the n type scaling in terms of the number of elements you need. Do you see that as being a problem for like computational efficiency if you go higher than 2 dimensions, or do you have thoughts about that?
I perfectly like the question. I see that as exactly follow-up work, and that's what we are doing. So the thing is that in this work, basically, we really use this whole geometric product, which basically operates, as you said, doesn't scale very well, especially if you go to higher order algebras. But it seems that there are other objects or other operations in geometric algebra, like, for example, the sandwich product, which basically is a reflection with a conjugate reflection. And that allows you to do like orthogonal transformation of objects of different algebras very efficiently. And that means that you might change a bit the representation, but it allows you, as you said, to go to higher order Clifford algebras, which gets interesting because there are many objects in computer vision, but also in, for example, MRI or astrophysics, which are like 6-7 dimensional objects. And for that, we're trying to develop. Yes.
I see. Yeah, thank you. It's very interesting.
Are there more questions? If not, thank you, Johannes, for this wonderful talk. And thanks for tuning in and taking your time out.
Thank you so much for having me. It was a great pleasure. And yeah, hope to hear and see some of you soon.
Sure. We will move to our second speaker, our second presentation. Suraj, Sharma, and Ashesh Pawar. Oh, I just mixed it. Yeah, I just mixed it up. Yeah, hi.
Yeah,
so I've made both of you the co-hosts. Could you try sharing the screen when I introduce you to the audience?
Sure. I think Ashesh is going to start with the presentation, maybe.
Okay. So in our second presentation, we would be listening to Ashesh Sharma and Suraj Pawar. They would be talking to us about towards deep learning for wind farm wake modeling. Suraj's expertise is in scientific machine learning and its application in computational flow physics problems. He received his PhD from the School of Mechanical and Aerospace Engineering at the Oklahoma State University. His doctoral work focused on the development of physics-guided machine learning algorithms for national renewable and for turbulence closure and reduced order modeling for turbulent fluid flows. He was a graduate intern at the National Renewable Energy Laboratory for the summer of 2021, where he worked on the development of deep learning-based surrogate models for wake predictions. Suraj is currently working as an artificial intelligence resident at the Shell Global Solutions. Ashesh is a computational scientist at the National Renewable Energy Laboratory, working on the development of simulation tools for next-generation wind farms. His research lies at the intersection of high-performance computing, numerical methods for PDEs, and machine learning. He is also a co-developer of several US DOE simulation tools, where he works on the performance portability for GPU-accelerated applications. He received his PhD from the Aerospace Engineering Science Department at the University of Colorado in 2017. His doctoral work focused on the development of numerical methods for shape and topology optimization problems applicable to energy storage and civil structures. With that, let's welcome him for both of them for the presentation. You may want to start.
Thank you for the, can you hear me?
Yes.
Thank you for the introduction. And glad to be here today presenting our recently published work. Like you mentioned, Suraj was an intern here last summer. Most of this work started back then, but we continued this collaboration as he went back to grad school. So the focus of the work is machine learning for wind farm wake modeling. I'll mostly be touching on the motivation aspect of it and then hand it off to Suraj to go a bit more into the weeds of the things. So starting off with the motivation, why do we care about wakes? Let's look at what has been happening in the industry for the past 4 to 5 years. So a few years ago, there were reports of farm-farm interaction causing reduced electricity production. Just for some context, for offshore wind farms, wakes can travel 100 kilometers. So when we say farm-farm interaction, there are going to be a lot of neighboring wind farms as we go offshore, and farm-farm interaction is a huge issue. Moving on to 2019, in an unprecedented move, the CFO of the world's largest offshore wind farm developer basically admitted that most of the underperformance could be attributed to inaccuracies with modeling. And this was mostly directed at capturing blockage. So blockage is the slowdown of the wind as it approaches a wind farm, and also the evolution of wakes within a wind farm. And basically an industry-wide discussion revealed every single wind farm was underperforming. So as recent as early this year, one of the world's foremost consultancies for wind farm development and operations pointed to velocity deficits and deep arrays resulting in underperformance. Deep arrays for wind farm translates to any turbine that sits beyond 3 or 4 rows of the first turbines within the wind farm. So the final news clipping is from August 2020. So as recent as a couple of months ago, apparently we are still not capturing the long range wake behavior accurately. And depending on whom you speak with in the industry, they might say everything is fine on the modeling end of things, or they might go on an endless rant. So it might very well be that the industry has solved some of these problems, but realistically, we honestly won't know up until about 5 to 6 years more, because there is little to no operational data from wind farms that were designed using the current generation of models. So that's what we want to tackle, wind farm flow modeling. So why focus on the predictive capability of farm flow models? Well, the obvious answer is you model the wakes correctly, and that translates to improved prediction of how the farm is going to behave. A non-trivial reason is the uncertainty associated with the energy production of a wind farm. That directly ties into the financing of the wind farm. And to give you some background on this, just to give you a holistic picture of things, the energy production of a wind farm is the most important criteria for bankability reports used for financing. And this estimate is usually simplified to a bell curve, helps the banks and investors to determine their risk. What it translates to is we want to focus on p-values. And essentially the p-value of interest is p50. So it's the production value that will be exceeded 50% of the time during a given period. It could be 10 years, it could be the entire life of the project. It varies. So energy predictions from pre-constructions have often not translated to similar levels during operation. And this discrepancy has been crucial to defining the uncertainty in p-values. Banks are so risk-averse that they won't even finance a wind farm based on this P50 value, which lies at the center. They will actually go to something that's the P90 or P95 and finance based on that. So you can imagine if a wind farm or if a financer is financing based on a value that's so low, well, that results in less capital or just higher rates of interest. So basically, at the end of the day, the difference between the P90 and P50 values, the left oval and the right oval, is what's referred to as uncertainty in bankability reports. And it can stem from many factors, but one of the biggest factors has been wake modeling and blockage. The other are not related to modeling, so we won't touch on that. We focus on farm physics, so wake modeling and blockage are what we are trying to address and improve. Reducing the uncertainty, like I mentioned, would result in higher capital invested or reduced interest rates, better financing terms altogether. And we are talking millions and millions of dollars in regards to just reducing this uncertainty by even 1 to 2%. In the ideal world, we'd have models where P90 and P50 are top of one another, but I don't know if that's going to happen. So talking of wind farm flow physics, there's a whole lot going on in a wind farm flow physics that affects the wakes directly. So one could say that wind farm physics span about 10 orders of magnitude, from hundreds of kilometers across neighboring wind farms to the order of microns in the boundary layer along the turbine blades. Everything from neighboring farm interaction to the capping inversion layer and the lower atmosphere effects, the formation of wakes, and that affects the eventual energy production in wind farms, which, as we saw, goes directly into the bankability reports. So we want to reduce the uncertainty of energy estimates of wind farm by capturing wake atmosphere interaction, long range wakes, so that's farm interaction, and basically have a whole around understanding of stability informed wake formation and blockage. And keep in mind, this is all in a very complex environment. So we're talking air-sea interactions, breaking waves in deep water, complex terrain of involving canopies and forests, and massive turbines. Turbines are getting so huge that they are beginning to interact with the lower atmosphere. So which brings us to where the industry is and what we are trying to address through our current work. So the industry has historically focused on engineering or analytical wake models. These are usually tuned to LES or operational data. This is the industry standard, currently runs on the order of seconds, and that works because usually when you're preparing these energy estimates, you have to run thousands of parameter suites, different wind directions, different turbulence intensities, different arrangement of turbines. So something that runs on the order of seconds works great. Order of minutes works great too. And that's the highest fidelity that's used in the industry currently, which is steady state RANS model. Usually they use a zero equation RANS model. Some developers do use the K omega SST or K epsilon models, but most of them use a zero equation RANS. They use actuator disk representation of turbines. To those who are not familiar with the concept of an actuator disk, it's essentially a disk representation of an entire turbine. So the entire swept surface of a turbine is replaced by surface forces that act upon the incoming flow. This can either be implemented at a rate corresponding to the period averaged mechanical work that the rotor extracts from the flow, or by using instantaneous values of tabulated airfoil data. What's not used in the industry is LES. And anyone who has done flow past a bluff body will know that wake characterization in LES is very different from what RANS gives you. So the actuator line model is used to represent turbines in LES, and actuator line model essentially represents each rotor blades as a line of radially varying force. The concept is similar to actuator disk, except you're resolving each blade as a line, so it requires more computational cost, close to real time on GPUs. And then we have the highest fidelity, which solves hybrid Ranselius equations, but hybrid Ranselius because it models the turbines with their actual geometries. So when you're resolving those microns boundary layers, you have to move to Rans near the turbine blades. We can model blade effects, erosions, and add-ons like vortex generators, icing packages, and whatnot. We can do this all in complex terrain, breaking waves, air-sea interaction, but requires several days to run on thousands of GPUs. So now all the modeling tools I presented, we have developed at NREL, and they span a vast variety of computational cost. The idea is to use the higher fidelity to inform the next generation of lower fidelity models, because there needs to be some kind of a trade-off between the fidelity and the computational cost, because using thousands of GPUs for days is just not tractable for the industry. So the need is essentially methods that can balance fidelity and scalability and inform the next generation of wake models. We want to essentially decrease the time to solution. This is where we hope to leverage deep learning, something that Suraj is going to talk about next. This was mostly a proof of concept study for which we considered analytical models with varying fidelity. And I'll hand it off to Suraj to take it out from here.
Oh, sure. Thanks, Ashesh. Let me share my screen. Okay, are you guys seeing the slides?
Yeah, we can see the slides.
Okay, just going to presentation mode. Okay. Let me put my point.
You are on the,
okay.
You probably have shared the wrong monitor.
Okay, let me try sharing again. Are you seeing the slides now, or
yes,
it's still the
slides? Yeah.
Okay, it's slide, right? Okay. Let me just start the pointer. Okay. Okay, so thank you, Ashesh, for the introduction, and also like talking about the motivation behind like why do we need to improve the existing engineering wake models that we have, and basically how improving those wake models can lead to have the better estimate of the annual energy production from the wind farm, but at the same time to design better controllers that will improve the efficiency of the wind farm and so on. So as Ashesh said, like this is in like a proof of concept study, and therefore instead of actually dealing with the very high resolution data coming from larger simulation or actual blade result simulation, we focused on the engineering wake models, and within engineering wake models also we have like different levels of approximations. So the two models that we used for our training or like for the data generation are like the Gaussian wake model and the curled wake model. Here I will just briefly describe how like those analytical wake models are being formulated. So the Gaussian wake model, which is kind of like a low fidelity representation of the data over here, is like basically derived using the simplified linearized Navier-Stokes equation. And one of the main advantage of these engineering wake models is that it can take physical parameters like turbulence intensity, wind direction, wind shear, wear, which can be directly measured within the field directly into account whenever we are doing things like layout optimization and so on. Also, like specific to the Gaussian wake model, it has a very few parameters which can be easily tuned either using field observational data or the data coming from larger simulation. So the way it is formulated is that the normalized wake deficit given over here, it is parameterized using the super Gaussian wake profile, and C of x tilde here is basically the maximum normalized wake deficit at distance x tilde. X tilde is the normalized streamwise distance downstream of a turbine. And basically we assume that the wake is going to have this Gaussian type of profile. And we can then parameterize the normalized maximum normalized wake profile at distance x tilde using this expression. So as you can see here, depending on the inflow wind speed, the coefficient of thrust of the turbine will be different. And additionally, we also need to determine two parameters, that is sigma tilde and n, which is again the function of streamwise distance. And those can be determined using the turbulence intensity or the parameter beta. And the parameter beta is again a function of the thrust coefficient, which depends on the things such as pitch angle of a wind turbine or the inflow wind speed. And this Gaussian wake model has those tuning parameters, like it has around 5 tuning parameters, which can be tuned using the LES data or the observation data. So the main limitation is that once you tune the model, it works very well for a particular site or a particular type of the LES data. But like those models might not generalize very well to a different site, or if the flow physics is very different. And therefore, like there is also another engineering wake models which has been proposed recently. It's like a curled wake model. And the curled wake model, it basically solves the linearized Navier-Stokes equation in time marching fashion. So what we do is like we start with the Navier-Stokes equation, then decompose the velocity into two components. The first component is the best solution, and the second component is the basically wake deficit or perturbation velocities. So the equation given over here, it's like once we decompose the velocity and make some assumptions such as steady state and like neglecting the pressure gradient and so on, we finally get this like an Navier-Stokes equation, which is then solved in a time marching fashion, but in the streamwise direction. So as you can see here, there is no like a temporal term, so it's still a steady state model, but like we will be solving it by marching in the streamwise direction. And basically depending on like there were some experimental data or experiments being done, which shows that whenever we basically yaw specific wind turbine, the basically the wake not only gets deflected, but the shape of the wake also gets changed, as seen by the some kind of a curled shape over here. But this is not like missing in the Gaussian wake model. As you can see over here, the profile is kind of very symmetric. So that was the main motivation behind the curled wake model. So if you want to have better controller or the better wake steering performance, this curled wake model is able to capture that curling mechanism better as compared to other engineering wake models. So the way it does is that basically use the Lambosian vortices, which are then initialized at the rotor, and those vortices models the curling mechanism. Using the magnitude of those vortices, we can get the tangential component of velocity ut, and basically the circulation, it's a function of again thrust coefficient and the yaw angle. And once we have this span-wise velocity v and the vertical velocity w, we just solve this equation to for the u dash, and that is nothing but a wake deficit basically. Okay, so those are the two models that we'll be using in our study. The Gaussian wake model, it's a low fidelity model, and the curled wake model, which is the high fidelity model basically. Okay, so let's look at like how do we construct our data driven surrogate model. We'll be having like two different types of a model. The first model, or like before discussing the surrogate model, I will just like define the problem statement. So basically the wake problem, we can write it as like given certain flow field parameters or the organization of the how the turbines are being arranged within the wind farm, the type of the turbine that that basically we are using. We want to determine the three-dimensional velocity field. For example, the flow field parameters can be wind speed, wind direction, a yaw angle, pitch angle of a turbine, or the turbulence intensity. So given those scalar parameters, we want to determine the velocity field in a three-dimensional region, which is downstream of the turbine. So if you are to write this like a more of mathematical form, we can basically say, given the scalar parameters, in our first study, we only focus on the three parameters, which are like most important. Those are the wind speed, u infinity, the basically the yaw angle, and the turbulence intensity. And then we want to determine the wake velocity in a whole three-dimensional domain. So before actually doing the training and so on, we try to see how to improve the robustness or generalization of model through feature engineering. So what we do is like, instead of using the inflow wind speed as the input feature, we replace it with the coefficient of thrust. And the main reason is like the typical coefficient of thrust for like the wind turbine looks like this. So usually after the design speed, the coefficient of thrust drastically starts reducing. And therefore having the coefficient of thrust as the input feature helps in making the model more robust and generalizes well. Additionally, we do not train our neural network to learn the wake velocity directly, but then we basically learn the normalized wake deficit. And this also helps in improving the generalization better as compared to learning the wake velocity directly. So those type of the non-dimensionalization and feature engineering we found like helps the model achieve the better and accurate results. The first model that we basically have is like a single feed-forward neural network, and basically it takes the input features as I discussed in the previous slide. But like a very naive approach to tackle this problem is to directly learn the whole three-dimensional velocity. However, it can be very high dimensional. The output space can be very huge, and that will basically lead to have a large number of trainable parameters, but also like a lot of time in the computation, like a training as well as deployment. So what we do is like we divide each of the training example or each of the realization data into multiple snapshot. And here basically each of this cross plane corresponds to single example. And therefore now our input feature is furthermore augmented to take the streamwise distance x also as the input feature. And the output is going to be normalized wake deficit at a particular cross plane, which is given over here. It is still a very high dimensional because a typical discretization in the span-wise and wall normal direction is in order of hundreds. Therefore, this output, this n is still around like more than 10,000. And we use dimensionality reduction techniques to basically tackle this problem, which we will be discussing in the subsequent slides. Okay. And so as Ashesh mentioned, like we also wanted to see, can we use the multi-fidelity data fusion approaches to tackle this problem, where the data from high fidelity model is used to inform the certain low fidelity engineering wake models. So when we were doing the literature survey, like we found there are like different methods available out there, which can basically do the data fusion for multi-fidelity modeling. One of the very popular method is like a Gaussian process regression. And furthermore, we can like learn the nonlinear relationship between low fidelity and high fidelity data. Another approach, which is also used in the literature, it's like a transfer learning. So what we do is like, first we train our model on the low fidelity data, and then we train basically again the model on the few samples of high fidelity data. One of the limitation of this transfer learning approach is that it assumes that there is a lot of similarity between the source data and the target data, which might not be the case in reality. For example, the low fidelity data and high fidelity data, both are coming from the different types of the distribution, and therefore we thought transfer learning might not be appropriate for this problem. We did some experiment with the Gaussian process regression also, but in our case, the output was very high dimensional, and we were not able to get very good results. But the third approach, that is the composite neural network, which is being used in our study, we found that was really giving a good results and also have the better generalization and so on. And I will talk in the next slide how does a composite neural network works. But there are some other methods also out there. For example, the work on like deep generative model, which basically learns the high resolution data conditioned on the low fidelity data, which is more of like a super resolution. So that is also another approach for the multi-fidelity data fusion. And more recently, the neural operators are also gaining a lot of popularity for the surrogate modeling. So there has been some work done on the multi-fidelity DeepNet, augmented further with the residual learning and the input features. So that is also interesting approaches that can be used in our future studies. So as I mentioned, like we basically use the composite neural network, which was proposed in this JCP 2020 paper. And basically what it has is like the composite neural network has like two parts. The first part is the low fidelity neural network, and the second part is high fidelity network. And the high fidelity network, it is further split into two components. One is the linear part and another is the non-linear part. And basically the other multi-fidelity data fusion approaches often assumes that there is a linear relationship between the low fidelity and high fidelity data. But like with composite neural network, there is no assumption like that. Basically, so the composite neural network can learn the nonlinear relationship between low and high fidelity data. And in order to learn the linear and nonlinear relationship separately, we have those two separate networks. And one of the main advantage of composite neural network is that you can do the training in the combined manner. That is, the low fidelity network and the high fidelity network, those are not trained separately, but like both the networks are trained together. So the way it works is that you have certain input features corresponding to the low fidelity data, and that is trained using all the large samples of the low fidelity data you have. And the prediction from low fidelity, it is further like augmented with the input features corresponding to high fidelity data, and then that is passed through the linear and nonlinear component of the high fidelity. And at the output, we just take the summation of those linear and nonlinear components. And for a problem, we are dealing with like a more of regression problem. So we just use the mean squared error as a loss function given over here. Okay. And as I said, like previously, even though we are just learning the velocity field in a particular cross plane, the output is still very high dimensional. It is in the order of 10,000s. So in order to reduce the number of trainable parameters, what we do is like we use the proper orthogonal decomposition. So once we have collected the data, like the normalized wake deficit for different combinations of the inflow wind speed, turbulence intensity, yaw angle, we then form this matrix A, where each column corresponds to the normalized wake deficit at distance x at a particular streamwise distance. And then we just do the singular value decomposition to identify the most dominant POD modes that are going to capture the most of the variance present in the data. And usually, typically, it is order of tens, the POD modes that are enough to capture around more than 95% of the variance of the data. And therefore, the neural network is then basically trained to learn the relationship between the input parameter space and the low dimensional representation of the data in the POD space. And during the deployment, once we have the prediction of those POD model coefficients, we can then reconstruct the velocity field using the pre-computed basis functions that we have stored in the offline data preparation stage. Okay. So let's look at how we generate the data, like how do we sample the data and so on. And then we will look at the results part. So basically, of course, like since we were dealing only with like three input parameters, that is wind speed, yaw angle, and turbulence intensity, we thought it would be better to just sample the low fidelity and high fidelity data uniformly with some time interval, with some interval. But once we have the input space to be very large, we can use techniques like Latin hypercube sampling or space filling that can basically sample the data more efficiently. But at least for a proof of concept stage, for the low fidelity model, we generate the data correspond to around 1600 cases, 1600 realizations. And for the high fidelity, we have the data corresponding to around 45 realizations. And once we train our high fidelity and multi-fidelity DNN models, we then test it for another 700 parameters, which are within the interpolation region. So we assume that we are not going to extrapolate a lot, and therefore we were mostly interested into seeing how does the neural network models behaves in the interpolatory region, basically. Okay, so once we have all the data generated for low fidelity and high fidelity model, we first do the proper orthogonal decomposition to see how many modes are capturing how much energy or the variance of the data, and decide the number of POD modes to retain. What we found is like for both the Gaussian wake model and the curled wake model, around 6 to 8 modes were enough to capture more than 99% of the variance in the data, and therefore we fixed the number of POD modes to 10 for both the Gaussian wake model and the curled wake model. And the figure on the right hand side shows the basis function for Gaussian wake model and also for the curled wake model. And it can be seen very clearly that the basis functions for the Gaussian wake models are more of the symmetric velocity profile, or the symmetric basis functions. But for the curled wake model, due to the curling mechanism that is being modeled, we see that the shape of the basis function is not very symmetric like the Gaussian wave model. So that was the main reason why, like, behind using the curled wave model, because it is able to approximate the physics better as compared to the Gaussian wave model. Okay, so with this, let's look at the results basically. So for the results, we basically visualize the velocity in the hub height plane and also at a cross plane at a particular distance from the downstream of the turbine. So the figure over here basically shows the velocity profile at hub height plane, the hub height of the basically the rotor, and the top row, it is for the true velocity, that is the curled wave model, and the second row, it is for the prediction that we have from those data driven surrogate model. The HFDNN corresponds to a single neural network, single feed forward neural network, and the multi-fidelity DNN corresponds to a prediction from a composite neural network. And on the basically the extreme right column just shows the intermediate prediction that we get from a composite neural network for a Gaussian wave model. And just to analyze how does the variation of the error looks like spatially, we like also normalize it with the inflow wind speed, and we find that like a normalized percentage error is well below 2%. For both the single fidelity neural network as well as composite neural network, and those results were for a yaw angle of 15 degree, which was not included in the training. The similar results are also seen for a like a yaw angle of minus 15 degree for again the inflow wind speed of 11 meter per second, and basically the observations are very similar. We also like compare the velocity field at a particular cross plane at distance x over d equal to 8 of downstream of a turbine, and we can see that the prediction from the basically the true, that is a curled wave model, and from a single fidelity and high fidelity and the multi-fidelity DNN, both are able to capture this velocity profile very accurately, and also the normalized percentage error is well below 2%. And this is again for the yaw angle of 15 degree and also the another yaw angle of minus 15 degree. And like while we were basically evaluating our results, it was quite difficult to really just by looking at those visualization plot can we really see whether the data driven model is able to do the prediction accurately or not. So that's why we came up with some of these physics-based metric to evaluate our data driven surrogate model. The metrics like mean squared error or structural similarity, which are very commonly used in machine learning, we cannot directly apply to some kind of a physics-based problem. So that's why we use this kinetic energy flux as basically kind of metric to evaluate whether the data-driven surrogate model is doing a good job or not. And the way we do is like we compute the kinetic energy flux at each of the downstream location, which is just obtained by integrating the like a square of velocity in that corresponding crossing. And once we have the kinetic energy flux from the true velocity and the predicted velocity, we then compute the relative percentage error. And like if this relative percentage error is well below certain limit, then only we can say that we have more confidence in our data-driven surrogate model to be actually used for layout optimization and so on. So let's look at how does the results for this kinetic energy flux matrix looks like. Here are basically this plot corresponds to turbulence intensity of 4%, and the right plot is for the turbulence intensity of 7%. And basically the x-axis it's for the streamwise distance, and the y-axis corresponds to certain inflow wind speed. And basically we can see that for all the yaw angles, that is minus 15 to 15, the normalized percentage error, it is well below 1 or 2%. Okay, let me just drink some water. And even if you go to like some other turbulence intensity like 12% or 15%, we see that the basically the percentage error for the kinetic energy flux, it is well below 1 or 2%. Therefore, like in conclusion, both the single fidelity neural network and the composite neural networks, those are able to capture this calculate the kinetic energy flux well below our tolerances, and like we have like more confidence in terms of the physics-based metric also. Okay. So this brings to like the conclusion and the future work basically. So again, like as Ashesh said, like wakes are very complex due to their unsteadiness, interaction with the atmospheric turbulence, and also the interaction from the other wind farms and so on. There are a lot of high fidelity techniques like large eddy simulation, blade result simulations available there. But like to do it for thousands of simulation, it is still computationally very expensive. And therefore, engineering wake models have been very popular to do things like layout optimization and for controlling the wind farms and so on. But still, there is a need to improve those existing wake models so that the uncertainty associated with the power prediction can be further reduced. And again, like the main motivation behind this study is that the way we approach this problem is using the data from high fidelity model to inform the reduced order model, which can be any of the engineering wake models. Yes. Towards that, we build like two deep learning models, and we found that both the deep learning models, that is a single fidelity neural network and multi-fidelity neural networks, both were able to learn the curled wake model quite accurately. And in terms of the computational performance, once we invest into the data generation and training, those models can achieve almost 1 to 2 order of magnitude computational speed up as compared to the curled wake model. From our results, as you can see, we do not necessarily always see that the composite neural network always give the better results as compared to a single fidelity networks. And we believe that there can be two reasons for that. The first one is maybe the curled wake model. It's relatively simple, and maybe a single feed forward neural network it's able to learn this relationship, especially once we do the POD to reduce the dimensionality of the velocity space and so on. Another reason can be that basically we use the mean squared error for the POD model coefficients as a loss function. So one can also investigate what happens if we reconstruct the velocity field from the predicted POD model coefficients and then use that mean squared error between the velocity as the loss function. So this is also something that can be investigated to really see how to get a better performance with the composite neural network. And last but not the least, I think there's still a lot of ongoing work to increase the complexity of data-driven surrogate model by including things such as wake-wake interaction, terrain interaction, and atmospheric stability impact. And before ending my talk, I'll just briefly describe some of the future work that is going on towards that. In the future work, we would like to move away from the proxy models. That is, instead of using these engineering wake models, can we use the data from large eddy simulation or the blade result simulation as a high fidelity data? Additionally, things such as actual field, the data from the field observations, like from the Met master LiDAR, how to ingest that data to inform the low fidelity models. That is also something like going on. And once we start increasing this complexity, the input parameter space is going to grow further. So how to tackle that is also part of the ongoing work. So just like towards that, one can also use machine learning for things such as inflow characterization. Because if you are not able to predict the velocity field upstream of the wind turbine accurately, then the prediction from any either computational model or a surrogate model, it's not going to be very accurate. Therefore, some of the machine learning techniques can also be explored for that. For example, in this work, physics-informed neural networks were applied to reconstruct the inflow velocity field. And the way they do is like they use the data corresponding to this LiDAR locations. The data is sampled at few points which lies along those like a LiDARs. And basically that they train the neural network using the data loss function, but also the Navier-Stokes equation as a soft constraint for training. And once we train the physics-informed neural network, then you can just do the prediction at any spatial location XY, but you can also do the forecasting in the time dimension also. So they were able to capture the evolution of flow structure as well as average vertical velocity, and so on. So like one is like we are also looking into using machine learning to characterize the inflow better. And another application where the multi-fidelity data fusion can be interesting, it is for the design of the airfoils. So the way typically the wind turbine design is being done is that we assume that there is certain candidate of airfoil shapes, and depending on the desired aerodynamic and structural performance, which can again come from the wake of the turbines, then we can select certain airfoils which satisfies those constraints. Another way to tackle this problem can be using an invertible neural network, which not only learns the forward mapping from shape of the airfoil to the aerodynamic and structural characteristic, but it can also learn the inverse mapping that given certain desired structural and aerodynamic characteristic, it can also recover the shape of the airfoil, which will meet those constraints, and this will finally lead to having the better optimal shapes for the wind turbine, which can be less expensive as compared to just selecting the airfoil from the predefined shapes. So I mean, like the more details can be again found in this paper. Yes. So with this, I will end my talk, and I would like to thank you all for giving us an opportunity to present our work at current seminar, and we'll be happy to answer any questions.
Thank you, Suraj and Ashesh. Let's have some questions from the audience. We have a lot of people who are working in the multi-fidelity domain.
Yes.
So Varun, you would want to talk about it? You're working on some similar topics.
Yeah, thanks for the talk, Suraj. I've been working on a similar topic using multi-fidelity networks to learn, from low fidelity and high fidelity data, learn the mapping. One of the things that I found interesting in your work was that you are training both your low fidelity and high fidelity model in parallel. I was wondering if you had tried using a pre-trained low fidelity network and then use the output from that to train your high fidelity network. How was that like in terms of training and accuracy?
Yeah, I think, very interesting question. I think we did not try it explicitly training the low fidelity network separately and the high fidelity separately, but like in our case, the training was done jointly. I think the main advantage is that if you train in isolation, the low fidelity and high fidelity, sometimes in the deployment, there can be some, basically the accumulation of the error from the low fidelity. So basically, I think this training in a joint fashion, it's like seems to be more accurate as compared to training in isolation. Otherwise, there will be kind of discrepancy in the way you train the high fidelity network and the way you actually use the prediction from a low fidelity during the deployment. So because during the training you assume that the low fidelity model is almost going to be perfect for training the high fidelity network, but like that might not be the case once we actually deploy from the low fidelity model. So one can also do things such as accounting for some errors during the training, but like this is not something we actually tried.
Okay. And another thing that I was probably thinking about asking you was, so you talked about how to generalize like the models that we have.
Yes.
So when you talk about parameters, how does it work? Like, do you have parameters for any site where you want to like test your model at, or is that an assumption that you have to make that these might be the parameters for your model?
Yes. So yes, I mean, we kind of like when we were in the initial stages, we fixed on what all parameters that we want the model to work on. For example, like we decided this is the range of inflow wind speed or yaw angle. So we kind of assume that we are always going to operate within that region only, and we will not be extrapolating a lot because I think it's always a little bit there can be some kind of an error, especially if you extrapolate a lot. And if you are again going to deploy those models in like the layout optimizations, where you are again going to run like thousands and more than thousands of cases, there can be some cases where the prediction can be really very bad. So that's why we decided to operate only within the interpolation region. So that was the reason, like our testing data was also coming within the interpolation region. That is the data on which the model was trained for.
Yeah, I see. Okay, thank you.
I hope that answers the question.
Yeah, it does. Thank you.
Yeah, thanks.
The two models that you presented on multi-fidelity, both are from this group actually.
Yes,
So
exactly. Composite environment.
We don't have Shuhui on call today, but we have Lulu,
Yeah, I think.
Yeah.
Yeah.
Lulu,
So
do you have something to share?
I know that they also recently have the paper on multi-fidelity DNNs, where they also use the residual learning and input augmentation. But I think when we were actually doing this work, the composite neural network was, we found it to be working better. But we haven't experimented yet with the actual DNN multi-fidelity.
I think he just went away.
Okay.
Maybe may I ask a question?
Yes.
So thanks a lot for the good talk. I'm curious that since it looks like you are trying to build an approximation form of the RANS model, so maybe like say by using multi-fidelity, can you capture like something, maybe the classical RANS model and have challenging also, for example, like the flow separation. Can you do flow separation with this multi-fidelity model?
Currently we were mostly focusing on the wake prediction problem.
I see.
Yes, but I think if you want to capture yes, Ashesh, you want to add?
Yeah, no, to answer your point, yes, flow separation is something that can be tackled, especially because I would actually say none of the RANS models can capture flow separation in the stall region. And that's where some of these newer models like IDDS models have actually shown promise, but even they falter in the stall region. And so we are actually looking at field inversion machine learning to basically find turbulence closures for the stall region. But outside the stall region, so for example, post-stall, that's much higher angles of attack. We are able to use a stock IDDS or even detached eddy simulation models to capture flow separation.
I see. Yeah, because you mentioned this INN, this kind of, design. Airfoil. I guess for the airfoil, the flow separation is kind of.
Yeah, no, absolutely. So field inversion machine learning is something that we are beginning to look at internally. We're not sure how that will go, but yeah, capturing the stall is a huge pain point even in the industry currently.
I see. Yeah. Thanks a lot.
Do we have more questions? Vivek, do you want to ask some questions on the airfoil flow that you've been studying?
No, the presentation was great. Thank you. Great talk.
Hi, I don't have any questions, but I just want to add something. So I was a visiting research fellow in with the Crunch group on June, July, I don't remember. So hello everyone. So the thing we are currently working on is a study similar to Sang and South that you mentioned at the end, with pins to reconstruct the wind field. So they did it for the inflow. We are doing it at the area of the wake, and seeing how those results go. It's a much more turbulent flow, and it has other things that are very difficult, but yet it's an interesting challenge. And that's it.
So if there are no more questions, thank you, Suraj and Ashesh, for tuning in today and for giving this wonderful presentation. We'll post the recording of today's video on our YouTube channel, which is the Crunch Group. And thank you everyone for tuning in, and have a great rest of the day and a great weekend ahead.
Thank
Bye.
you.